Hi, my name is Raul Machado. I'm doing the second assignment presentation. Okay. Okay, the first exercise, part A, is about generated data sets. As you can see here, this data set that only shows the first 6 realization for the covariates, the propensity score, the treatment or control, the errors, Y0, Y1, potential outcomes, and the observable variables, okay, y, the consistent assumption, okay, and then the estimation of the average causal effect with the simple inverse probability weighting estimator is 8.421, and an IPW estimator with normalized weights is 15.00 based on the question provided equation, okay. As an extra, the average causal effects obtained directly, estimated one, from the this table is around 15.899. As you can see, the second estimator gives closer values on the first one. I should point out that with the current low value of n equal 1,000 individuals, and without a fixed or common fixed random number generator, like if you use a set seed for R, some of the values presented in this work might vary, but conclusion like which parameter is smaller or closer to who remains the same. The part B is to use a sample version of the expression in equation 30 of the paper. Okay, the sample version of the expression in equation 30 on the assumption that the propensity score is known is this is to the question, okay, and are used to investigate the variance of the first and the second estimator respectively, and the solutions, the results are 11.090 for the first one and 0.083. And the estimator, the second estimator, had the smallest variance, because it was part of the question. The question was which estimator had the smallest variance. This one, okay, the second one. And remember this 1.083 because will be seen later on, as you can see here, 1.055. Okay. Here in C, make simulations with 1,000 replicates of the first estimator and second estimator to evaluate the variance of the two estimators in 2B. If the propensity score is known, are the estimators variance affected? First, I did the replicate, and they have the two distributions from which they get means. So simulation of the 1,000 replicate of the first and second estimator. I see this question 1 and 2 in the C in the assignment, which are the same as equation 7 and 8 in the paper. Okay, the results are presented as histograms below, as you can see here, where their means are 15.894 and 16.046, and their variance are 11.364, and notice this is very close to the previous one, 1.055. Again, the result from the second estimate have the smallest variance. Hence, the variance with the propensity score is known, like the one from equation 1b, are close to the variance obtained here in equation 1c here. Hence, estimator's variance are not remarkable affected if the propensity score is known. The D part. Using the table in the data in 1 and exercise 1a, estimate the average treatment for affected treated, this one, with estimators provided in the assignment. The average, the results are, the first one gave me 20.158 and the second one 9.039. But notice that that reading from the table equivalence would be 9.993, very close, the second one. That is estimators to give the solution closer to this one rather than the first estimator, okay? This is reading directly from the table, okay? It's a subset, okay? It's based on the treated, okay? I mean the average treatment effect of the treated. So these are very close. This and this too, okay? Exercise number 2. Show the sample means of the covariates x1, x2 for treated and controls in a reweighted sample of the data generated in process 1 using the weight variable as seen here. So this is the estimated propensity score using the package survey and table 1. I want to point out certain things here. For instance, this is about the propensity score weighting. Hence, it would be a good idea to see the distribution of propensity score for treated and controls in order to find out if all the subjects have some positive probability of receiving either treatment, I mean control or treated. This translates in overlap between the controls and the treated. The figure below shows a good overlap. As you can see, overlap here. Both there is a red, which is a treated, and the control blue. Where is a red, there is a blue. Even if that extreme, we can get more of one group than the others. For instance, we have more red than blue here, and more blue than red. Still, there are some in the opposite group. You see, even on this more red and blue, still there are some blue here. Okay. And notice that the mean here is a little bit higher than for the treated and the control. This is not asking it in this problem, but I just pointed that out. The requested result stratified by treatment, that is control and treated, is shown below. Before reweighting, in table here, before reweighting and reweighted in table 3 here. Note the difference between the number of controls and treated in table 3. For instance, let me change it. See then, you see, it's a 566, while it's a 434. One I reweighted is very close to each other, okay? Just to let you know. Okay? And this is smaller. Here is smaller than here. Also, this is important. The standardizing mean differences here is way larger than 0.1, and here is 0.1. Here go from 0.8 to 0.1. Here from 0.1 to less than 0.1, which is what we're looking for. So we want always the standardized means difference to be smaller than 0.1. So we should improve this. For instance, increasing the number of individuals. Okay. And then the exercise 2 B part is about showing this mathematically, okay? So I'm gonna show you, this is explained by itself, but let me go through a little bit about it. Show that the expectation, this is the weight, this is the treated, and this is one of the covariates, okay? Notice that it says this is covariate for treated and control, okay? So we're done with J1 and 2, that is, this is for the treated and this is for the control, okay? So note that the weights when it treated is 1, I mean, if we aren't treated, okay, it's become this part, which is the same upon 1 minus t equals 0, which means this part is 0, of course there will be 1 here. And for the controls, it's the opposite. This will be 0, and this will be 1, so you get this, which is equivalent to put that this is equal 1, and of course it will be equal 0. Okay, so now what we do is that the original equation here becomes, and this is now going to do for treated first, okay, just by step. Put it treated here, and then you get the indicator here, and then you get the part of the treated, and of course double expectation. I recall that the x depends on x1, x2, so you put out to take out everything you know from the conditional expectation, put it out. But this inside expectation is not only that the estimated propensity score here, and they cancel each other, and you get this. The equivalent for the second part, for the control part, as you can see here, okay? And also, I won't take this because it's very easy to read. I'm running out of time. And the same for the case when we deal with this part, okay? So this is a summarizing, you get this proof, okay? Thank you for your attention.